What 18th century French nobleman, one of the fathers of modern chemistry, was sent to the guillotine in the Reign of Terror during the French Revolution? He was branded a traitor for reasons that included supporting an Italian-born mathematician considered an enemy to the French. In the late 1700s, controlled scientific experiments gave rise to laws about the nature of matter. Antoine Lavoisier, a member of the French aristocracy, dedicated himself to the study of the elements. Through his experiments, Lavoisier discovered the law of conservation of mass, which states that in a chemical reaction, the mass of the products always equals the mass of the reactants. About the same time Lavoisier was sent to the guillotine, French chemist Joseph Proust proposed a second law, called the law of definite proportions. It states that if a chemical compound is broken down into its separate elements, the masses of the individual elements will always have the same proportions. For example, a water molecule is always 2 atoms of hydrogen and 1 atom of oxygen. This means that all samples of a given compound have a constant composition of elements, regardless of how much material you have or where it came from. Water is water, regardless of its source. It is always 2 parts hydrogen and 1 part oxygen. The law of definite proportions is important in writing balanced chemical equations. If you want to react twice as much hydrogen, then, because of the law of definite proportions, you know that you have to react it with twice the oxygen, and that it will produce twice as much water. Changing one part of the chemical equation changes all other parts in proportion. Constant composition also means that if the composition of a molecule changes, then the substance changes to something different. Add an oxygen atom to a water molecule, and you have hydrogen peroxide, a different substance with different properties. Humans need water to survive, but consuming hydrogen peroxide is harmful to us. Gargle with water and you won't taste much. Gargle with hydrogen peroxide and you will experience a bitter taste. Take care with subscripts when writing chemical equations. If you leave off or change the subscript on an element in a chemical equation, you have changed the substance. As scientists continue to study relationships among elements and compounds, they found other laws that describe how compounds are formed. In 1805, English chemist John Dalton answered a question posed by many at the time. Why does the decomposition of certain compounds form the same elements? He found that different compounds formed from the same 2 elements have a proportional relationship. This led Dalton to propose the law of multiple proportions, which compares compounds that are composed of the same elements, such as water and hydrogen peroxide. The law of multiple proportions states that when the same 2 elements combine to form different compounds, the different masses of the first element, in this case oxygen, that combine with a fixed proportion of a second element, in this case hydrogen, are in a ratio of small whole numbers. Both water and hydrogen peroxide are made up of a fixed amount of hydrogen, 2 atoms. However, each differs in its number of oxygen atoms. Hydrogen peroxide has twice as many oxygen atoms as water. Therefore, the ratio of the mass of oxygen in hydrogen peroxide to the mass of oxygen in water is 2 to 1, which is a small whole number ratio. We can use the law of multiple proportions to compare 2 compounds formed by the reaction of nitrogen and oxygen. The first compound contains 9.80 grams of nitrogen and 22.40 grams of oxygen. The second compound contains 16.80 grams of nitrogen and 9.60 grams of oxygen. For a given mass of nitrogen, what is the simplest whole number mass ratio of oxygen in the 2 compounds? The law of multiple proportions states that different masses of the one element combine with a fixed mass of a second element in a ratio of small whole numbers. To compare the masses of oxygen with a fixed mass of nitrogen, we divide the mass of oxygen in each compound by the mass of nitrogen. This gives the mass of oxygen per 1 gram of nitrogen for each compound. Now that we have the different masses of oxygen for a fixed amount of nitrogen, we can set these numbers in a ratio. Looking for a whole number ratio, we simplify. The simplest whole number mass ratio of oxygen in the two compounds is 4:1. The calculated ratio means that the mass of oxygen in compound 1 is 4 times greater than the mass of oxygen in compound 2. This ratio could also be interpreted to mean that a molecule of compound 1 contains 4 times more oxygen atoms than a molecule of compound 2 for a fixed number of nitrogen atoms. There are about 114 known elements that combine in different proportions to create millions of compounds with different properties. The law of multiple proportions is important in balancing chemical equations and in predicting quantities involved in the reactions that produce compounds. Recipes give the proportions of ingredients that must be used in order to create a dish. How is a chemical equation like a recipe? When a chemical reaction occurs, substances change chemically to form new substances. During a chemical reaction, the substances that undergo a chemical change are called the reactants, and the substances that result from the reaction are called the products. For example, during photosynthesis, carbon dioxide and water are converted to glucose and oxygen. Carbon dioxide and water are the reactants, and glucose and oxygen are the products. Chemical equations describe chemical reactions. Just as a recipe describes the types and amounts of the ingredients necessary to make cookies, chemical equations help describe the types and amounts of the substances that are involved in a chemical reaction. A chemical equation also shows the direction that a reaction progresses. This direction is represented by an arrow that separates the reactants from the products. Reactants are to the left of the arrow, and products are to the right. If there are 2 or more reactants or products, they are separated by a plus sign. Chemical formulas are always used to represent the reactants and products. This equation has 4 chemical formulas. Notice that each chemical formula in the equation is followed by a letter in parentheses that represents its state: solid, liquid, gas, or aqueous solution. An S indicates that the reactant or product is in a solid state. An L indicates a liquid state, and a G indicates a gaseous state. An AQ indicates an aqueous solution, which means the reactant or product is dissolved in water. The number in front of a reactant or product is called a coefficient. The coefficient is a whole number and, usually, is omitted if the value is 1. The coefficients represent the smallest whole number ratio of the amounts of all of the reactants and products in a reaction. This ratio is similar to how a cookie recipe would call for 2 eggs for every 1 cup of sugar in order to get a dozen cookies. The coefficients indicate the number of molecules that are required for a chemical reaction to occur. In the chemical equation for photosynthesis, the coefficients indicate that 6 molecules of carbon dioxide and 6 molecules of water are required to produce 1 molecule of glucose and 6 molecules of oxygen. Coefficients are important when counting the number of atoms of an element on either the reactants or products side. For example, how many hydrogen atoms are on the reactant side in this equation? The ammonium ion, NH4, in ammonium phosphate contains 4 hydrogen atoms. The subscript outside the parentheses indicates that there are 3 ammonium ions in the formula for ammonium phosphate. The coefficient in front of ammonium phosphate indicates 3 formula units of that compound. The result of multiplying these is 36 hydrogen atoms on the reactant side. The coefficients can also be used to represent the number of moles required. So the coefficients show that 6 moles of carbon dioxide and 6 moles of water are required to produce 1 mole of glucose and 6 moles of oxygen. After the analytical balance was developed in the late 1700s, scientists began to study the mass of reactants before a chemical reaction occurred and the mass of the products after a chemical reaction occurred. These scientists discovered a unique trend. The mass of the products equaled the mass of the reactants. The scientists developed the law of conservation of mass to summarize this observation. The law of conservation of mass states that mass is neither created nor destroyed during a chemical reaction. It is only rearranged. The law of conservation of mass can be represented with the following formula. The total mass of the reactants equals the total mass of the products. Whatever goes into the reaction must come out of the reaction, so it is important to account for all atoms. Chemical equations illustrate the law of conservation of mass. The chemical equation states that 6 molecules of carbon dioxide and 6 molecules of water produce 1 molecule of glucose and 6 molecules of oxygen. If we compare the number of carbon, oxygen, and hydrogen atoms on the reactant side and the product side, we see that they are equal. We can count 6 carbon atoms, 18 oxygen atoms, and 12 hydrogen atoms on each side of the equation. Remember that the coefficients can also represent the number of moles of reactants and products that are involved in a reaction. We can convert moles of each reactant or product to masses of each by multiplying number of moles by molar mass. 6 moles of carbon dioxide multiplied by the molar mass of carbon dioxide, 44.009 grams, are equal to 264.05 grams. 6 moles of water are equal to 108.09 grams. Adding the masses of the reactants gives 372.14 grams of reactant. On the product side, 1 mole of glucose is equal to 180.156 grams, and 6 moles of oxygen are equal to 191.988 grams. Adding the masses of the products gives 372.14 grams. The total mass of the reactants equals the total mass of the products. When a chemical equation correctly reflects the law of conservation of mass, it is said to be a balanced equation.
You are making chicken soup for 6 people using chicken stock, chicken, carrots, celery, and a few spices. How can you be sure that you'll have enough soup to feed each of the 6 people a tasty 2-cup serving? Feeding a 2-cup serving to each of 6 people would require making 12 cups of soup. To produce 12 cups of soup, you have to begin with 12 cups total of ingredients. This means you'll have to decide what amounts of stock, chicken, carrots, celery, and spices you want to use to produce a soup that is flavorful and filling. Sometimes it is necessary to find the unknown coefficients of the reactants and products in a chemical equation so that it supports the law of conservation of mass. This is called balancing the equation. To represent the combustion of propane, we first need to write a general equation, sometimes called a skeleton equation. It has to have the appropriate chemical formulas, separated by plus signs, for the reactants and products. It also has to have letters and parentheses to indicate the states of each, and an arrow to separate the reactants from the products. In this case, propane gas, C3H8, is combusted with oxygen to produce carbon dioxide gas and water vapor. The skeleton equation only shows the molecules involved in the reaction, not necessarily the correct number of each. Notice that there are 3 carbon atoms on the reactant side and only 1 on the product side. Atoms of hydrogen and oxygen are also not balanced. When the number of atoms of each element on the reactants and product sides is not equal, the equation does not support the law of conservation of mass and is not a balanced equation. In order to balance the equation, we can multiply the reactants and products by coefficients that will equalize the number of atoms of each element on each side. A good method for balancing chemical equations is to add coefficients to metals and then polyatomics. Leave hydrogen, oxygen, diatomics, and water for last, because they typically can balance easily. Notice there are no metals or polyatomic ions in the equation, only carbon, hydrogen, and oxygen. Starting with carbon, the leftmost element, we see 3 carbon atoms on the reactant side, but only 1 carbon atom on the product side. Multiplying the CO2 molecule by the coefficient 3 gives a balanced number of carbon atoms on both sides. The next element in the equation is hydrogen. There are 8 hydrogen atoms on the reactant side of the equation and only 2 hydrogen atoms on the product side. Multiplying the water molecule on the product side by the coefficient 4 gives 8 hydrogen atoms on the product side, which balances with the 8 on the reactant side. There are 2 oxygen atoms on the reactant side. On the product side, the 3 carbon dioxide molecules each contribute 2 oxygen atoms for a total of 6. And the 4 water vapor molecules each contribute 1 oxygen atom for a total of 4. Cumulatively, there are 10 oxygen atoms on the product side. Multiplying the oxygen molecule on the reactant side by the coefficient 5 gives 10 oxygen atoms, which balances with the 10 on the other side. Always double-check the equation to make sure it is still balanced after all of the coefficients have been added. On the reactant side are 3 carbon atoms, 8 hydrogen atoms, and 10 oxygen atoms. On the product side are 3 carbon atoms, 8 hydrogen atoms, and 10 oxygen atoms. The equation is balanced. When balancing the equation, we added coefficients, but we did not change any subscripts found in the chemical formulas. Never change the subscripts of the chemical formulas in order to balance an equation. Changing a subscript changes the chemical formula and the composition of a reactant or product. Here are a few suggestions for balancing equations. Balance one element at a time. Balance metals and then polyatomics, leaving hydrogen, oxygen, diatomics, and water for last. And never change the subscripts in a chemical formula.
Is it possible to predict what will happen to elements and compounds when they are combined? If they do react with one another, how do scientists figure out what happened in the reaction? There are 5 major categories of chemical reactions, and most reactions can be classified in one of these categories: synthesis, also called combination, decomposition, single displacement, also called single replacement, double displacement, also called double replacement or metathesis, and combustion. Understanding these common reactions helps you predict molecular formulas for the products that come from different types of reactants. You can use the molecular formulas to create a skeleton equation and then balance the equation by finding the correct coefficients. Synthesis or combination reactions occur when two or more elements combine to form a single product. A plus X yields AX. For example, carbon reacts with oxygen to form carbon dioxide. The only possible reaction between two elements is a synthesis reaction. Another familiar example of a synthesis reaction is when carbon dioxide combines with water to form hydrogen carbonate, the carbonic acid that makes bubbly soft drinks. Again, A plus X yields AX. Once you write the skeleton equation, you can check to see if it is balanced. With 2 hydrogen atoms, 1 carbon atom, and 3 oxygen atoms on either side, the equation is balanced without adding coefficients. A decomposition reaction is the reverse of a synthesis reaction. A decomposition reaction is different from all other types of reactions because it is the only one with a single reactant. One substance decomposes to form 2 or more substances. AX yields A plus X. When carbon dioxide decomposes, it forms oxygen and carbon. When carbonic acid, H2CO3, decomposes, it forms carbon dioxide and water. Single displacement reactions are home-wrecker reactions. A single element breaks up the relationship between the elements in a compound. A plus BX yields AX plus B. Single displacement reactions occur when a more active element, in this case A, replaces a less active element, in this case B. On a reference sheet, you may find an activity series like this that shows which elements are more active. In a single displacement reaction, an element that is higher on the activity series will replace an element that is lower. Calcium is more active than cobalt, so when it is combined with a compound that contains cobalt, a reaction occurs in which calcium replaces cobalt in the compound. Magnesium is more active than aluminum, so it replaces aluminum in the same way. Once you write the skeleton equation, you can balance it to get the correct coefficients. An element that is lower on the activity series will not displace an element that is higher. Therefore, a reaction will not occur. Notice in these reactions that the more active element, calcium, is already part of a compound, so a reaction does not occur with either of the lower activity elements. Some single displacement reactions involve diatomic halogen molecules replacing halides. A halide is an ion that forms when a halogen atom gains an electron. The halides are fluoride, chloride, bromide, and iodide. These reactions also depend on the activity series, with fluorine as the most active and iodine as the least active. In a single displacement reaction, a diatomic molecule of chlorine will replace the 2 bromide ions in sodium bromide to form sodium chloride and bromine. Once you write the skeleton equation, you can balance it to get the correct coefficients. In a similar reaction, a diatomic fluorine molecule will replace 2 iodide ions in calcium iodide to form calcium fluoride and iodine. A double displacement reaction is sometimes called a double replacement or a metathesis reaction. In this reaction, the cation-anion pairs switch partners. Double replacement could be called the disappointing prom date reaction. A goes to prom with X, and B goes with Y. but A leaves prom with Y and B leaves with X. The general form of a double replacement reaction is AX plus BY yields AY plus BX. Double replacement reactions occur when two ionic compounds interact in aqueous solution. You can use the general formula to figure out what compounds will form, but one of the products will always be a precipitate, an insoluble salt, a gas, or a molecular compound such as water. A solubilities table like this one allows you to predict which ions will form precipitates. Use the solubilities table to predict precipitates. Sodium iodide reacts in solution with lead-2 nitrate to produce a lead-2 iodide precipitate and soluble sodium nitrate. Notice that the first cation always ends up with the final anion. Sodium phosphate reacts in solution with calcium chloride to produce soluble sodium chloride and a calcium phosphate precipitate. Once you write the skeleton equation, you can balance it to get the correct coefficients. The final type of reaction is combustion. When you hear combustion, you probably think of fire. A combustion reaction generates heat and light. Combustion reactions typically involve a hydrocarbon, which is a molecule containing carbon and hydrogen and oxygen gas. A complete combustion reaction produces carbon dioxide and water vapor. Once you know the type of hydrocarbon involved in the combustion reaction, you can balance the equation to figure out the correct coefficients for oxygen as a reactant and carbon dioxide and water as products. Larger hydrocarbon molecules such as cyclohexane and octane will require more oxygen for combustion and will produce more carbon dioxide and water.
You pour two clear colorless liquids together in lab and find that where the two liquids meet, a bright yellow color appears. 10 minutes later, you examine the flask and find that a solid product has fallen to the bottom of the solution. Describe what you think has happened. You have witnessed a double replacement reaction, in which two reactants, aqueous lead-2 nitrate and aqueous potassium iodide, produce soluble potassium nitrate and a lead-2 iodide precipitate. A precipitate is a solid product that settles out of a liquid during a chemical reaction. During a double replacement reaction, the reactants ionize, so that 4 ions are moving around in the solution, surrounded by water. Here, sodium iodide and lead-2 chloride are mixed, and the solution consists of sodium ions, iodide ions, lead-2 ions, and chloride ions floating around in water. When two ions, such as lead-2 and iodide, bump into each other and form a compound that is insoluble in water, the compound falls out of solution as a precipitate. In this reaction, sodium and chloride ions remain in solution, and insoluble lead-2 iodide forms and falls out of solution. The reaction is complete when precipitate no longer forms. Double replacement reactions are sometimes written as ionic equations. An ionic equation shows all the particles as they exist in solution. The ionic equation for this reaction shows all of the reactant ions as they exist in solution and the two product ions, sodium and chloride, along with a solid precipitate, lead-2 iodide. Note that each coefficient corresponds to the number of individual ions present. In the ionic equation, the sodium ions and the chloride ions are both reactants and products, which means they don't participate in the reaction. These are called spectator ions. chemists can write another equation called a net ionic equation that shows only the particles that participate in the reaction. In a net ionic equation, all spectator ions cancel. The net ionic equation shows that 2 aqueous iodide ions plus 1 aqueous lead-2 ion produce 1 solid lead-2 iodide. You can use a solubility chart to predict which reactions will produce precipitates and which reactions will not. The AQ represents an aqueous solution, which is prepared by mixing a soluble salt, such as ammonium bromide, with sufficient water to dissolve the salt. The S represents a solid, or an insoluble compound that settles out of aqueous solution. Solids are precipitates. For example, a reaction in aqueous solution can produce lead bromide as a precipitate. To predict the products that will come from a reaction, begin by identifying both reactants on the solubility chart. This skeleton equation shows aqueous lead-2 nitrate reacting with aqueous potassium iodide. Now, draw lines out from the reactants. The places where these lines meet are products. You can predict that aqueous potassium nitrate will be one product, and solid lead-2 iodide will be another product. You can also predict that lead-2 iodide will be the precipitate. Once you have the complete skeleton equation, you can balance it to get the correct coefficients in a balanced equation. Use the solubility chart to predict the products from the reaction of sodium chloride and magnesium iodide in aqueous solution. First, identify the reactants on the chart. Then draw lines from each reactant toward the other. The 2 places they meet are the products. According to the solubility chart, you can predict that this reaction will not produce a precipitate. You can also reverse this process to find reactants that will produce a particular precipitate. To produce iron 3 phosphate, you need a soluble phosphate and a soluble iron compound. Iron 3 bromide, iron 3 chloride, iron 3 iodide, and iron 3 nitrate are all soluble in aqueous solution. You can predict that any of these would combine with aqueous ammonium phosphate to produce an iron 3 phosphate precipitate.